Cool. Let's get started. Hi, everyone. My name's Shawn, and today I'll be talking about deploying Alluxio on Kubernetes and how to use Container Storage Interface plugin, CSI, with Alluxio to power AI and machine learning training. Okay, so first, let me briefly introduce what role Alluxio plays here. Alluxio is a data orchestration platform, which is able to unify all your data that may be stored in different storage systems. For example, AWS S3 or Google Cloud Storage, and cache them into memory. Then Alluxio exposes the data to our computing engines. So reading data will be a lot faster because they're reading from memory, not from cloud anymore. In AI and machine learning environments, it is very common that the training jobs read data directly from local file system. Alluxio Fuse exposes the data just as regular files stored in the machine, so that the training jobs, for example, PyTorch or TensorFlow, will still read the data from file system the same as before, but with memory speed. Another common practice in the training world is to deploy the services on Kubernetes. So let's take a look at how Alluxio is deployed in the cloud-native way. First, we have a master pod, which runs Alluxio master and job master inside. Of course, if we are using high availability mode, there will be multiple master pods, but we won't focus on that part today. In fact, we won't talk about too much about Alluxio master. Then we'll have worker pod, which runs Alluxio worker and job worker inside. Alluxio worker is where the data is stored. Finally, we'll have Fuse pods, which runs Alluxio Fuse process. Before moving on to how application, aka training jobs, and Alluxio interact, I want to talk about how Alluxio cluster is set up. By default, both worker and Fuse pod are started as daemon sets. What that means is each instance in this Kubernetes cluster will have one worker pod and one Fuse pod. Of course, you can choose to only put them on some of the instances with some configurations, but this is the default way. Plus, they're always co-located. Where there's a worker pod, there will be a Fuse pod. Now let's see how data flows from Alluxio to application. First, on the host machine, we'll have worker pod and the Fuse pod. The Fuse pod will have a bidirectional mount to a volume, which means that the volume and the corresponding directory inside the Alluxio Fuse container are basically the same thing. So anything happens on one side would happen on the other side. So when application pod comes in, it will mount this volume into its container as its storage. When the training job starts to read from data inside this volume, the request will be sent to the Alluxio Fuse. So I'm omitting a lot of details inside this underlying calls, but eventually, when the requests arrive Alluxio Fuse, the Fuse container will know, okay, someone needs this file. So let me talk to Alluxio worker and send a request for that file. The worker will then find the data that the Fuse container asks for and give it to the Fuse pod, which passes them back to the application. This traditional way of deploying has some benefits. First, the performance is better because of the data locality. Data is stored in Alluxio worker, which is on the same machine as the Fuse pod and application, so there won't be too much internet flow. Second, it is easy to deploy. By using help chart, one command can start them all: master, worker, Fuse. However, it also faces some challenges. First, Fuse pod starts along with the Alluxio masters and workers, so it's always up running and taking resources like CPU and memory, but it's not always needed. For example, some users reported that when they do data pre-processing, they read data from another Alluxio API, not through Fuse. So during this time, Fuse is not needed, but it's taking resources and slowing down the data preparation process. Second, a lot of AI and machine learning training are done with GPU, which doesn't have a lot of storage spaces for worker. But Fuse pod has to be on this machine with GPU for Alluxio to work, which is very different from what our traditional setup looks like, that worker and Fuse are co-located and on all instances. This needs non-trivial manual work to configure where the pods should go. So here is where our CSI container storage interface kicks in. So a little bit background about what it is. CSI doesn't only apply to Kubernetes, but we'll only focus on how it works on Kubernetes today. So volume is the storage for Kubernetes pods. And we know there are many storage systems wants to be used by Kubernetes. For example, here I include AWS EBS, Azure Disk, Azure File, Ceph, etc. Now, since this volume is a concept defined by Kubernetes, every storage needs to write code so that Kubernetes is able to use them. Then the Kubernetes team has to review their code and do iterations. This is a very inefficient because there are so many of these storage systems. Also, it's not like after the codes get merged, it can be directly used. They have to wait until the next Kubernetes release. Storage systems want this process to be faster. To solve this problem, CSI becomes a layer between the Kubernetes volume and the storage systems. It implements the volume interface and defines its own interface and telling all storage systems, as long as you implement my interface, I can make you the storage for Kubernetes. Now, their code doesn't need to be merged into Kubernetes code anymore. And so long as they implement the interface of CSI in their CSI driver, they can be used immediately. Now everyone's happy. Today, there are more than 100 CSI drivers out there, but the direct volumes, there are only less than 20. Now let's look at the first version of Alluxio CSI driver and how data flows. I'm not including the Alluxio worker here, mainly because in many cases, worker won't be on this GPU machine. So first, we need this CSI components. Then user will create their persistent volume and its claim. These are one type of the direct volumes that Kubernetes developed themselves. By using some configurations, CSI knows it is affiliated with the persistent volume and the claim. Finally, the application pod is created. It basically mounts the persistent volume into its container as the storage. CSI is aware of this mount. So before it actually gets mounted, the CSI driver will first spawn an Alluxio Fuse process. Bidirectional mount the persistent volume to a specific directory inside the Fuse container, where Alluxio Fuse is in charge. So after this Fuse process is ready, then the persistent volume will be mounted to the application pod. When application finishes its job, it will not use the persistent volume and the claim anymore. The CSI will know this, and it will stop the Fuse process. So quickly rewind what the challenges we are facing with the traditional setup. So Fuse is wasting resources while not being used, and they're not supposed to be set up everywhere with the worker. So now with this CSI driver, Fuse process lifecycle is the same as the application pod. Only when application is up, the Fuse process is up. And when the application is done with its job, Fuse process is done as well. This perfectly solves our problem. Plus, it is still easy to deploy. By adjusting some configurations in the Helm chart, we can still use the Helm chart command to start everything. And then the Fuse process is automated by our CSI driver. This is a solid improvement. However, this first version of our driver still faces its own problem. Most importantly, our fuse process is inside one of the CSI components, specifically node server. The node server has its own functionality. Now, what if the node server hits some problem and the whole pod is killed? Or we need to upgrade our CSI component, during which we have to shut the node server pod down. As we can see from this graph, in both cases, we lost the node server, and thus, at the same time, lost the fuse process. So the volume is still there, but it can't talk with Alluxio anymore, and it can't get data. The running training job can't find data, so it will fail. The training job might already run hours, even days, so stopping it like this abruptly, basically wasting a ton of time. Nobody wants to see this. This is why recently we made a change to our CSI driver to solve this problem. So this new version of Alluxio CSI driver, we still set up CSI components and create the persistent volume and its claim as before. Then when application pod comes in, our CSI driver, instead of launching the Alluxio fuse process inside the node server container, it will create a whole new pod with the fuse process running inside. This is done by using Kubernetes API. In other words, we take the fuse process out from the CSI components and put it into its own new pod, which our driver creates. Now, looking back at the problems we were facing with the first version of CSI driver, as we can see here, although the node server for some reason is down, the Alluxio fuse pod is still up running and continue to serve data. So for our next steps, first, we want to implement the fuse pod resource allocation. What I mean here is that now all the fuse pods are sharing the same configurations, including memory and CPU. But of course, different jobs will need different resources. So we want to make sure that we can allocate suitable resources for these training jobs. Second, in some cases, different applications always use different fuse processes. That's basically because of the same reason that applications need different resources, and we want to give different processes to it. So also special thanks to our community users who helped a lot on these projects, including Kevin Tsai from Ant Finance, Hui Fei and Haoning Sun from Shopee, and Binyang Li from Microsoft. Okay, that will be all. Thanks for watching.
All right. Thank you, Shawn. Appreciate it. So I do have a question. Yeah. Can you please just give an example of where the multiple applications in the same machine, and then if they start different fuse pods and then use different processes, or do they share the same fuse pod?
Okay, so the thing is, whether using the same fuse pod or not currently depends on whether they are using the same persistent volume and its claim. So for example, say we have two different data sets stored in Alluxio, and the application one wants to use the data inside directory A, and the second application wants to use the data stored in directory directory B. So they will need to use different persistent volumes to make sure they only see their own data. They don't want to see, well, unnecessary data for them. In that case, the CSI will know, well, you are using different persistent volumes, so I will spawn different fuse pods for you. But if the two applications are using the same data set, the Alluxio CSI driver will see, well, you're using the same data set, so you will share this fuse process. So basically, whether spawn new fuse process or fuse pod depends on whether they're sharing the same data set or the same persistent volume and claim.
Cool. Thank you. I think it looks like that's all the question for now. Thanks, Shawn. Appreciate